Hello, this is the last material in Module 2, our enolate chemistry module, Module 2, Video 2. Some loose ends to tie up. So we're looking generally at esters being involved in enolate reactions, and we have the intramolecular Claisen condensation, which apparently was different enough that it became another name reaction, the Diekmann condensation. So starting from a symmetric diester here, we have addition of base, formation of the enolate here in the standard way, and then this is set up for intramolecular reaction. So presumably only 1 molar equivalent of base is added so that you get enolate formation at only one of the two sites. So the electron arrow pushing internally would be classic enolate reactivity as a nucleophile, and forming a bond to the carbonyl carbon of the ester, then the abbreviated sort of all in one step. Well, here I didn't do it all in one step, pardon me. So that brings us to the structure below, right here, where the new bond has formed from 2 to 7, right? There's the new bond from carbon 2 to 7. So the bond in enolate chemistry is almost always from carbon 2, the alpha carbon adjacent to what was the carbonyl, to another carbonyl carbon. That's what we're seeing here. And then to finish up that second step, which I got ahead of myself, kicking off the OET leaving group, which is fine because it's in OET base, and you get your final product, ring formation. So it is an annulation or ring forming reaction, the Diekmann condensation. So another version of ester enolate chemistry, now including the Michael addition in it. So this doesn't have its own name, I suppose. Basically, it's a Michael addition where you're using esters. And so again, starting with a symmetric diester, here we're going to have enolate formation. And in this case, I'm just going to do the simpler form of the enolate right here. Sometimes it's easier to see what's going on there if the first few times you're doing stuff. So here's an anion that's going to form a bond in conjugate addition, Michael addition fashion. So going back to the Michael addition in previous presentations, bond forming, bond breaking, bond forming, bond breaking, leads to the important new carbon-carbon bond right there, going below. And then protonation of this enolate usually happens like this from the alcohol solution that it's in. Bond forming, bond breaking, bond breaking, bond forming, bond breaking. And that gets you to this final product, which of course, is set up for much more chemistry of interest, either doing chemistry on a ketone, which is different from esters here, or on either ester group. This relates to what we saw in the in-class session recently on the Sadovine synthesis, which is posted on Canvas as a handout. It was the first step in that synthesis. Basically, it's very similar, an intramolecular Michael addition in that case. I want to wind up with something of scholarly interest, but also reinforces Aldol chemistry. So Aldol condensations actually take place in nature, believe it or not. And we're looking at collagen, which is a fibrous component of skin, bone, tendons, cartilage. There's probably over 20 different types of collagen, but they all basically are composed of 3-stranded polypeptides. So there's one of those here, one of those here, and then they sort of create these bundles of fibers, but they can be altered by these crosslinks to give them different tensile properties. So the number of crosslinks leads to different tensile properties. In other words, how strong are the strands in the bundle together? If they're cross-linked, how elastic are they, and so forth. So it gives the physical properties. The way these cross-links form is in a chemistry familiar to us, except for this first step. So a lot of things in biological reactions occur with enzymes. The first step is that these amino acid side chains end up where you have similar amino acids on each side of the two strands. Those can get oxidized to aldehydes, as you see here. Enzymatically, an enolate can be created in the next step on one or the other of these side chains, these altered side chains. Now the enolate is set up for, yeah, you guessed it, Aldol reaction, right? Intramolecular, I guess you could say. No, I guess this would be intermolecular. Sorry. So that bond will form from carbon 3 of the enolate to carbon 4, as I numbered them here. So there's the new bond right there, forms as we see below. Leads to this structure. Elimination in just the same way that we see in the Aldol condensation, like Aldol condensation, final step, like in the Aldol condensation. And there we have the eliminated water, the double bond forming there. This is what comprises crosslinks in collagen. They're Aldol condensation crosslinks that lead to those different properties for all the different kinds of collagen. So pretty interesting. Like the Achilles tendon is more rigid and somewhat less flexible, whereas like a rat tail is super flexible. Those are both collagen, having different numbers of crosslinks. So it's great to be able to get to some of this more interesting stuff later in the sequence of organic chemistry.